So we are talking lesson 2, part 1. And specifically, we're going to be talking about the sampling distribution for a sample mean. All right. So that means every sample that we take, we're going to find the mean and plot it. All right. So this is like our pinky example from yesterday. Or if you guys, hopefully, you guys watched the AP Stats Guy video. This was about the, I think, people who love tacos, I think it was. I'm not sure. But hopefully you guys watched that video. And we're talking about the sample mean in this lesson. Lesson 8.3, we're going to be talking about sampling distribution for a sample proportion. All right, so just so you guys know what's down the pipe, we have sample mean for today, okay, and tomorrow. Next week, we're going to be talking about for the sample proportion. All right, so we're going to be focusing on these two sampling distributions. All right, can you read this one out for us? Evan, read this example out for us, please.
The campus of Pasadena City College has a fish pond. Suppose there are 20 fish in the pond. The length of the fish in inches are given below.
Keep going.
Suppose we randomly catch a sample of 3 fish from this pond and measure their length. What would the mean length of the sample be?
Awesome. Thank you. Okay, guys. So what I want you guys to do, and let's play a little game. Look at these 20 fish. Don't use a calculator, but I want you to estimate the mean just by looking. Let's see how close you can get. So in the chat, go ahead and put down what you estimate the mean of these 20 fish to be just by looking at those numbers. All right, go. Okay. Okay, 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 okay. Good. Okay. Yeah, this is just a guess. You are just straight up guessing a mean just by looking. I see how close you can get. Let's see if anybody gets it. Okay, okay, okay. Okay, okay. Oh yeah, try not to cheat by looking down at the notes. If you looked, it's okay. Don't worry about it. All right. And now everybody's going to look. All right, good. All right, now go ahead and look at your notes down towards the bottom, and it says the true mean is 8. All right, some of you guys got it right on. Good job. I got 1, 2, 3, 4, 5, 6 people who guessed 8. Good job. Okay, so the true mean of these 20 fish is 8. Good guessing. Okay. Now, let's say we, grab 3 fish at a time and we collect a sample. All right. And this is the first sample we get. We got the 6.3, we got the 2.2, and the 13.3. We happen to catch these fish. This sample mean is 7.27. What is this actually called? This sample mean, this value I got from the sample. This is a what? Aaron. This is a what? What is that called? A value calculated from the sample.
A statistic.
Yes, good job. Which happens to be the name of our class. So good thing you know what that means. Okay, so value calculated from a sample, that is called a statistic. Nice. All right, let's do another one. Let's say we catch 2 more samples of 3. So caught another 3 fish, got a mean of 6.23. All right, so that's another statistic. And let's grab another sample of 3 fish, got a mean of 10.78 inches. All right, and that's our statistic. Again, the true mean is 8. Notice, none of our means from the sample are actually 8, right? Some are close, some are pretty far. So what is this called when I have all these like different values from these samples? Andrea, what do you think? What is that called when I get these different values from different samples? 2 words.
The sampling distribution.
Oh, first word is close. Not the second one. This is not the graph yet. This is just the fact that you get different values from different sample, and they're not all 8, right? Not all the means of the samples is exactly the population mean of 8. So the fact that I have differences from each sample is called, I'll give you a hint, Andrea, 2 words. First word starts with an S. Second word starts with the V. The first word I think you got. What did you say the first word was?
Sampling.
Sampling. Okay, and the second word starts with a V. And by the way, if you think you know the answer, feel free to plop it in the chat. Oh, some of you guys are pretty close. Start with a V. Think about a word that means like differences, but starts with a V. Yeah, some people are getting in the chat.
Is it variation?
There you go. Nice. You got it. Nice. A lot of you in the chat are giving me different versions of the word variability. So that works. Okay. But I'm gonna say this is sampling variation. All right. Or sampling variability. You can go that way too. All right. So sampling variability. I like that. Sampling variability. All right, good. So that just means that you get different values depending on the sample you get. Okay, nice. All right, now, if we were to like spend forever fishing, okay, there are actually 1,140 different possible samples you can get from this lake of 20 fish, all right? So of size 3. If we were to actually catch all these different samples, and we were to calculate the mean length of each sample and plot all those means, what would this graph be called? Jonathan, what would that be called?
Something plot.
No, it's not something plot, but it is 2 words. Okay, it's a graph of all the sample means. A graph. So I took a sample, found the mean, plotted it. Found another sample, found the mean, plotted it. And I did that for every possible sample. And I made a graph out of all those means. What is that called? 2 words. Good. People are putting stuff in the chat.
I'm not sure.
Okay. First word starts with an S. Second word starts with a D.
Sample distribution.
There you go. Yeah. Our lesson from yesterday. Okay, so sampling distribution. That's what this entire chapter is about. So make sure you know that vocab. Good, people in the chat. Nice. All right. So yeah, this is a sampling distribution. That is the graph of all the sample means. Okay? All right, great job. Let's get into today's stuff now. We have 4 rules when it comes to a sampling distribution for sample means, okay? Here we go. Rule number 1. We talked about this in the homework with number 6. The center of your sampling distribution will be at the population mean. Okay, that's what this stands for. All right. So if you guys remember yesterday's graph, right? It's a pile of X bars, it's a pile of means. And where that's going to be centered at is going to be centered at the population mean, like the average pinky size of our entire class, right? Would be the center of this graph. So actually, let me help you guys out with this, because I know it's a little bit tricky with all these, Greek letters, notation. It could get a little tough to understand. So let's put this in words. So this guy represents the mean of the sampling distribution. Okay, so that's that whole thing, mean of the sampling distribution. Versus this guy is the population mean. Okay. So again, this just means that our graph yesterday with our activity, our right-hand side graph is going to be centered at the same spot as our left-hand side graph, our population graph. All right, so that's rule number 1. All right, the mean of the means is the mean. That's what that means. Mean of the means is the mean. All right, let's try the rule number 2, talking about spread. All right, so for spread, this guy is our standard deviation of the sampling distribution. Okay, so this is the standard deviation of the sampling distribution. All right. So how spread out the sampling distribution will depend on 2 things. Notice we have 2 variables here. Okay. This top one is our population standard deviation. And then this guy here, N, stands for our sample size. Okay. So hopefully that makes more sense now with those labeled. Okay. So notice that the population standard deviation does matter, but we divide that by the square root of the sample size to get the standard deviation of our sampling distribution. Okay. And you guys saw this on the video yesterday with the AP Stats guy. Any questions? Go ahead, unmute yourself or put it in the chat. Okay, those are our first 2 rules. We got 2 more rules to go. I'm gonna clear this out unless you stop me. So either unmute yourself or put in the chat if you don't want me to clear it. In 3, 2, 1. Okay, let's go on to the next one. All right, read this out for us, please. Jasmine, please read this out for us.
The paper mean platelet volume in patients with metabolic syndrome and its relationship with coronary artery disease. Thrombosis Research 2007 includes data that suggests that the distribution of platelet volume of patients who do not have metabolic syndrome is approximately normal, with mean equals 8.25 and standard deviation equals 0.75.
Nicely done. Great job reading all those medical terms too, by the way. You did way better than I would have. All right, so you have this distribution of the population. All right, so these are all individuals. Mean of 8.25, standard deviation of 0.75. Okay, so look at that population distribution. It's normal, unimodal, symmetric. Okay, now what we're gonna do is we're going to use a computer generator to randomly sample from this population. Okay, so we're going to start with taking samples of 5. All right, so we take samples of 5, find the mean. Sample of 5, find the mean. We're going to do that 500 times with the computer generator and make a sampling distribution. Okay, and I already did that, so this is what this looks like. At the top left, this is our sampling distribution with sample sizes of 5. Okay, And we did 500 of these samples to make this graph. Now, if we were to do it again, but this time sample size 10, that's what this orange one looks like. And then sample size of 20 is the green or teal one. And then sample size of 30 is the mustard yellow one. Okay, so these are the sampling distributions from this population, just with different sample sizes. Okay, so I have a few questions for you guys. Number one, what do you notice about the means of these histograms? Means, meaning where are they centered? What do you notice about where the means of these histograms are, where they are centered? Let me go ahead and ask Nina, what do you think? What do you notice?
They're some of them are different.
So give me like a number. Where do you think, like the one in blue, where does that center look like it's at?
12.
Where?
12.
Wait, 12. 12's
Oh,
not
sorry, I'm looking at mine. Like 8.3.
8.3. Yeah, like 8.2, 8.3. Yeah, right. We're on the notes, we're at the top left of the second page. Top left. Okay, nice. What about the orange one? What does that look like? It's centered.
Around like 8.2.
Okay, all right. And then what about the teal one?
8.2.
Okay. And then what about the last one?
8.2.
Okay, so what do you notice about the means?
They're the same.
They're all pretty much the same. Yeah. In fact, they are all equal to 8.25. So great estimating. All right. All the means are at 8.25. That's rule number one, right? They're all centered at the population mean. So great. Okay. So we notice that they're all centered at the same spot at 8.25. Okay. Thank you, Nina. Let's go to the next one. What do you notice about the standard deviation? Standard deviation. Bella G, what do you notice about the standard deviation as n is increasing?
Well, the standard deviation. Wait, is n the standard deviation or no?
No, n is the sample size. So looking at the graphs, when I ask what do you notice about the standard deviation, I'm talking about the spread. So as you're going through the histograms, the blue to the orange to the teal to the mustard yellow, what do you notice about the spread?
Well, as it like is less spread out, the standard deviation goes up or down.
Yeah. So what is standard deviation?
Isn't it like if you have a mean, like the distance like between the numbers?
Good. Yeah, it's the average distance from the mean. So as things get closer to the mean, is the standard deviation going up or down?
Down.
Down. There you go. All right. So perfect. So what we notice about the standard deviation is that it is going down. It's decreasing. So as n is increasing, the standard deviation is decreasing. All right. Now look at the rule number 2. That should make sense. Looking at the formula here, the standard deviation on the left, right, is this formula on the right. As your n is increasing, that denominator is increasing, your whole fraction lowers in value as that denominator goes up. So that goes with rule number 2. Good. All right, thank you, Bella G. And lastly, what do you notice about the shape of these histograms? The shape. So I'm talking about like symmetry, about the shape. Bella E, what do you notice about the shape?
The more samples you collect, the more like symmetrical it becomes.
Nice, good. And I mean, even at the very beginning, like this blue one on the top left, what would you say that one looks like? Is it skewed? Is it symmetric? What would you lean towards?
I would say symmetric.
Yeah, I would too. I think they're actually all pretty symmetric. All right. Good. So what I noticed about the shape of these is that they're all roughly symmetric. Okay. So that actually is rule number 3. And rule number 3 is saying that when the population, the original distribution, is normal, the sampling distribution is also going to be normal. All right, so the population distribution is normal. The sampling distribution will also be normal for any sample size, even when it was a small sample size of just 5 or a larger one of 30. Okay? All right, any questions on that? All right, let's get into our last rule then. And let me see. Oh, there's a picture for you guys. So you can kind of see how it changes as n increases. All right, center, exactly the same. Spread is decreasing. All right, and then they're all symmetric. Okay, let's go into our last rule. Let me get Will. Will, can you read this one out for us?
The paper, is the overtime period in an NHL game long enough? American Statistician 2008 gave data on the time in minutes from the start of the game to the first goal scored for the 281 regular season games from the 2005 to 2006 season that went into overtime. The density histogram for the data is shown below.
Thank you, Will. Nice. I don't know if there's any hockey fans in this class, but I actually never really watched hockey until I married my husband, who is a big hockey fan. So, interesting sport. I'm getting more into it. All right. So, here are the 281 values of that overtime time. Okay. And notice it is definitely skewed right. Right. Mean of 13, median of 10. All right. So skewed right distribution. Okay. What we're going to do is we're going to do the exact same thing. I have a computer generated histograms of different sampling distributions with sample size 5, 10, 20, and 30. Okay. So this is what it looks like with the different sample sizes. Same population though, right? This is the same population we're drawing from. The only difference is how big of a sample we draw every time we draw a sample, okay? So first question, still the same. What do you notice about the mean? All right, so look for the center, guys. Look for the center for each one of these guys. Approximate it. And let me go to Tiffany. What do you think? How do the means compare?
They're roughly like the same, around like 13.
Yeah, perfect. They're all about 13, which again goes with rule number 1, right? The means are all the same as the population mean. So roughly around 13. Perfect. What do you notice about the standard deviations? Malika, what do you notice about the standard deviations?
You could say that the spread of the data becomes less as the sample size increases.
Perfect. I think that was the best way to say it, so I'm not even going to say anything after that. Okay, so yes, we see that. And lastly, let's look at the shape. Okay. Oh, actually, I will repeat it just in case somebody missed it. So as the sample size increased, the standard deviation decreased. All right, as the sample size increased, the standard deviation increased. All right, great job, Malika. All right, and lastly, let's look at the shape. Let's go Diana Wang. What do you notice about the shape of the distributions?
It's pretty evenly spread, like pretty symmetrical.
Like which one are you looking at?
Kind of all of them.
All of them? Okay. What I notice, I do agree that they seem roughly symmetric, but I would say not always. Like if you look at the blue one, all right, I know there's a lot of like peaks and stuff, but in general, that doesn't look exactly symmetric to me.
So like right skewed or
Yeah, I would
okay.
say right skewed. And then if you go to the orange one, it's still little bit, right? And at what point does it look actually fairly symmetric?
The yellow one.
Yeah, I would say the yellow one looks fairly symmetric. Even the one in teal, slightly right skewed still. So, good job, Tiffany. Nice. The thing about this, guys, is that with the shape of the histogram, it actually is a little more right skewed because the population was right skewed. The population was right skewed. So that's why my sampling distribution isn't always normal, but it got more normal as n increased. So that's actually a big, big deal. Okay. Because even though our population wasn't normal, it was right skewed, severely right skewed. Even though it was right skewed, the sampling distribution could still be normal as long as my sample size was large enough. Okay, so this was such a big deal, right? Such a big discovery that they labeled this a theorem. Okay, that's how important it is. It is a theorem, guys. All right, so this is called the central limit theorem. And basically, it states that even though your population, even though it's not normal, your sampling distribution can still be normal if your sample size n is sufficiently large. Okay, so that is the central limit theorem. All right, so here's your picture. Population started off really skewed and increased to 4, got a little less skewed, and increased to 16, less skewed. That actually looks fairly symmetric, pretty normal. Okay, any questions about the theorem? Because that is a key point there. Okay, all right. So the question I actually would have is, what's considered sufficiently large, right? That seems very, very subjective. All right, so I will let you guys know there is a magic number. All right, there is a magic number to how large a sample size needs to be considered sufficiently large enough for the central limit theorem. So I am curious what you guys think that number should be. So in the chat, go ahead and put down a guess. What do you think that magic number is going to be for it to be sufficiently large for the sampling distribution to be approximately normal? That's a good guess. Uh-huh. Okay. Wow. That's very large of a number. All right. Okay. All right. Interesting. Decimal. Okay. It is a whole number. Okay. It is a whole number. Let's see who can get the closest. All right. So what sample size do you think will be sufficiently large enough to make sure that our sampling distribution is approximately normal? Okay. So far, I have everything ranging from 10.5 to a million. Okay, I will let you know the answer is in between those numbers. Okay, good. Okay. Oh, no one's got it yet though. No one has hit the number. There is one magic number. Okay, well, it's more than one. It's more than one. One is definitely too little. Oh, all right, somebody hit the magic number. Nice. Nice. Okay, here we go, guys. The magic number, congrats to the person who got it, is 30. That's it. Some of you guys definitely have a really high standard with the really, really high numbers. It's actually just 30. Yeah. So what this means is, as long as your sample size is at least 30, right? 30 or more, it doesn't matter how skewed your population is. Your sampling distribution will be approximately normal. That's huge. All right. So again, as long as you're sampling at least 30 at a time, even if your population is skewed, your sampling distribution will be normal. And notice I've abbreviated it to be the CLT because we actually use this quite a lot. So CLT, central limit theorem. Just think of it like a BLT, like the sandwich, but with carrots instead. I don't know, you're going healthy. All right, so carrot, lettuce, and tomato. Question in the chat, why 30? Great question. The reason why they landed on 30, all right, this is just kind of like a known standard thing. It's not just like me thing. Just from trial and error, right? From computer generated stuff, we noticed that at 30, the distribution was approximately normal. So going back to that, right? Once we reached 30, it got pretty close to normal. So that's why the magic number is 30, just from trial and error. Good question. All right, so highlighting that central limit theorem, very, very big concept in statistics. All right, guys, that is it for our lesson. So one last thing, I do want to show you guys this visual about the sampling distribution. I think sometimes students do better when they see like the entire picture all on one page. Okay, so usually in class we would do like a matching game, but it's kind of hard to do that with distance learning. So I'll just go ahead and tell you guys what each part of this means. Okay, so this top part, this is the population distribution that we draw from to make our sampling distribution. Okay, so this right here, oops, is our population distribution. Here, this row, these are a bunch of sample distributions. Okay, so there's a bunch of them. So this is a sample distribution. This is a sample distribution. This is a sample distribution. Okay, so that's taking a sample and like just graphing the sample. And here, this is the sampling distribution. All right, so that's where we find the mean from each sample and we plot it and make a new graph called the sampling distribution. Okay. Yeah, I just wanted to put this up here because sometimes it helps students to see all of that process with the vocab all on one page. So if you want to screenshot this, I know this isn't in your notes, feel free to screenshot that. And that way, hopefully it's helpful to see the whole process.